In a previous lesson we introduced heating curves. So let's review that briefly. We have a heating curve shown here where we have the solid phase transitioning into the liquid phase, and then we're warming up the liquid, then we're boiling the liquid, then we're warming up the gas. Or we could go the opposite way. We could start with a gas and condense it into a liquid and then cool that liquid down and then freeze the liquid and then cool the solid like that. Whenever we're on a sloped portion of the heating curve, we're going to have to use the delta T form of the equation with a specific heat capacity. That is a heat capacity that is specific to the solid or the liquid or the gaseous phase. If we're in the midst of a phase transition, for example, freezing or melting or boiling, then we would need to be using the equation that's in the lower right that I've boxed in green. There is no temperature change during that transition, and we would need to use a constant, C sub F, the heat of fusion, or C sub V, the heat of vaporization, that is specific to the phase transition we're going through. Find the enthalpy change when 82.4 grams of ice at negative 13.5 degrees Celsius turns to water at 72.8 degrees Celsius. In the upper right, we have the 5 constants that apply for water. We have the heat capacity of the solid, liquid, and gaseous phases, and then we have the heat of fusion and the heat of vaporization. What I like to do is draw a quick sketch of a heating curve. We know that for water, the freezing point and melting point, the normal freezing or normal melting point, is 0 degrees Celsius. You should commit that number to memory. Similarly, the normal boiling point of water is 100 degrees Celsius. You should commit that number to memory. Where are we starting on this heating curve, and where are we going to end up? Well, it says we're at ice at negative 13.5 degrees Celsius. So clearly that's going to be below 0. And we're going to end at 72.8 degrees Celsius. Up here is 100, and down here is 0. So 72.8 is somewhere about there. What we're going to do is we're going to need to make a calculation to warm the ice to 0 degrees first. And I'll designate this with a triangle. And on the curve, that will take us from our green dot right here to the bend in the curve right there. In other words, to go up that little bit, we need to calculate a given amount of energy. We're going to use the delta T form of the equation because we are within the solid state of matter. I don't have room, sorry, to put the units on there, but you check and make sure that the units all look right. 82.4 grams. And then we've picked the specific heat of ice, which is, according to this table, 2.077 joules per gram Kelvin. And then the temperature change for this little portion of the curve, we want to go final minus initial. Well, final is 0 degrees minus negative 13.5. We're not going to go all the way up to 72.8 yet. We just have to make this little jump right here, and that's going to take about 2310 joules of energy. From that point, we now need to melt the ice. We need to add more energy to melt the ice. So I'm going to designate that little transition with a diamond shape. We can mentally imagine that we're scooting across this horizontal bit of the heating curve. For this part, we don't want to have the delta T form of the equation because there is no delta T. We need to use the other form of the equation, an amount of substance multiplied in this case by the heat of fusion, and I had to choose if the sign was positive or negative, and I know that in order to melt ice we have to put energy in. Again, we check the units, 82.4 grams, and then we pick the heat of fusion right off the table, 333 joules per gram, and that's about 27,439 joules of energy to make that change. And lastly, we now must heat the water from 0 degrees up to 72.8 degrees. I'm going to designate this little transition with a star. If we look at our heating curve, we're imagining that we're starting right now at this point, and we need to proceed up to the red dot. We're in a slanted portion of the curve, so there is a temperature change, so we use the delta T form of the equation. In this case, we have the specific heat of water. In the upper right corner, you can see it's 4.18 joules per gram Kelvin. The temperature change for this transition is final 72.8 minus 0, because for that change, the initial temperature was 0. And we get a number, 25,000 and change. The total enthalpy change will be the sum of those, and I've converted it into kilojoules.